Electricity and magnetism aren't two forces. Watch. A neutral wire makes a compass spin, move past the same charges, and a new force appears out of nowhere. How can motion create a field and still be real when physics can't depend on who's watching? Most people carry two separate pictures in their head. Picture one: electricity, charges, sparks, batteries, stuff that shocks you. Picture two: magnetism, a totally different force, bar magnets, fridge magnets, compass needles, some mysterious magnetic thing that only certain materials have. And we tolerate that split because everyday life lets us. Your socks crackle in winter, electricity. Your phone sticks to a magnetic mount, magnetism. Two different drawers in the brain. But physics hates that kind of messy bookkeeping. Nature almost never gives you two unrelated tricks that just happen to fit together so perfectly. When you see that, you should get suspicious. Here's the suspicious part. Electricity and magnetism are welded together so tightly that you can't even define one without accidentally inventing the other. You can start with a purely electric situation, just charges sitting still, and then simply change your point of view, move past them, and suddenly you will measure a magnetic effect. Not because the charges changed, not because a magnet appeared, because you changed. That's the whole claim we're going to make sense of. Magnetism is what electricity looks like when relativity is not negotiable. Now, that statement sounds like a slogan. It's dangerous as a slogan, so we're going to earn it slowly with a problem you can feel in your bones. Think about a straight wire carrying current, nothing exotic, a boring copper wire. It's sitting on a table plugged into a battery. The current is just electrons drifting. Very, very slowly, by the way. In a household wire, the electrons crawl millimeters per second. Yet the light turns on instantly because the electric influence, the field propagates through the circuit quickly. Different story. Now bring a compass near that wire. The needle turns. That's magnetism. It circles the wire. No magnet in sight, just moving charge. So here's the first problem. Why should motion create a new force? If electric charge is the source, then why isn't the electric field explanation enough? Why do we need a second field, a magnetic field, as if space has two different kinds of invisible wind in it? You might say, well, moving charge makes a magnetic field. That's the standard line. But that line is not an explanation. It's a restatement. It's like saying opium makes you sleepy because it has a dormitive virtue. Great. What is that virtue? So we push, take the same wire, put a single charged particle nearby, like an electron, and ask a clean question. If the electron is just sitting there, not moving, it feels no magnetic force from the wire. Magnetic forces don't push on stationary charges. They only push sideways on moving charges. But electric forces do push stationary charges. If there were an electric field from the wire, that electron would accelerate straight toward or away from it. Yet the wire is overall electrically neutral. The copper ions are positive, the electrons are negative, and they balance. So in the wire's rest frame, the net electric field outside is basically zero, and the action we see is magnetic on moving charges sideways. That already smells like something about frames, because moving is not absolute. It depends on who you ask. The electron can be stationary in your lab frame, but if you ride along with the drifting electrons in the wire, that same nearby electron is now moving in your frame. And suddenly, by the usual story, magnetic forces should appear or disappear depending on the observer. Wait, forces can't depend on who's watching. The particle either accelerates or it doesn't. An observer can describe it differently, but the physical outcome has to be consistent. So we've cornered ourselves into a second problem. How can magnetic forces be real if they depend on motion, and motion depends on the observer? That's the crack where relativity crawls in. Because relativity is not just about fast rockets and science fiction time dilation. Relativity is a rule about how space and time are stitched together so that different observers can disagree about lengths and times, but still agree on what actually happens. And electromagnetism, the whole electricity and magnetism package, was basically the reason Einstein was forced to take that stitching seriously. Light didn't fit in the old Newtonian picture. So if magnetism is tied to relativity, we should be able to see it in a situation where the only mystery ingredient is that different observers measure different densities of charge due to relativistic length contraction. That sounds abstract. Let's make it concrete. Look again at the current carrying wire. In the lab frame, the positive ions of the metal lattice are basically fixed in place. The electrons drift, the wire is neutral overall, so outside the wire, no big electric field. Now imagine a positively charged test particle moving parallel to the wire. In the lab frame, it feels a magnetic force toward the wire depending on direction of motion. That's the classic moving charge near current effect. Now switch frames, right along with the test particle. In this moving frame, the test particle is at rest, and a magnetic force can't act on it. Magnetism doesn't push on a charge at rest. So in that frame, if the particle accelerates toward the wire, it must be because there is an electric field. But in the lab frame, we said outside the wire, no electric field, neutral. So which is it? Is there an electric field or not? The answer is neutral is not invariant when charges are moving. The wire being neutral depended on a balance of two charge densities, positive ions and negative electrons. Density is charge per unit length, and unit length is not the same for different observers when things are moving. Here's the key physical point, and it's so simple it's easy to miss. If you have a line of charges moving relative to you, the spacing between those charges along the direction of motion is measured differently. That's length contraction. Same charges, different measured separation, different density. So in the frame moving with the test particle, the electrons in the wire are not drifting slowly anymore. They have a different velocity relative to you. The ions also have a different velocity relative to you. In general, the positive and negative charges do not share the same motion in that frame. That means their densities don't transform the same way. One set may look slightly more squeezed along the wire than the other. And if the densities don't match anymore, the wire is no longer electrically neutral in that frame. Neutral in one frame, slightly charged in another. Not because charge appeared out of nowhere, total charge is conserved, but because per unit length is a measurement, and the unit length is not absolute. So the moving observer sees a small net electric field around the wire. That electric field pushes on the test particle, now at rest in that frame, and produces the same physical acceleration that back in the lab frame we described as a magnetic force. Same event, two descriptions. In one description, no electric field, but a magnetic field acts on a moving charge. In the other description, an electric field exists, and it acts on a charge at rest, with no need for magnetism at all. This is not poetry. This is bookkeeping that has to work out, or nature would contradict itself depending on who's watching. Now, if you're honest, there's still a big discomfort here, because you're thinking, okay, fine, but magnets are sitting still. A fridge magnet is not a current-carrying wire attached to a battery, and my compass needle turns even when I'm standing still. So how can magnetism be just a moving observer trick? Good. That's exactly the problem statement for the rest of this story. We have 3 puzzles to resolve, and if we don't resolve them, this magnetism is relativity line is just clever marketing. Puzzle 1. How can magnetism be explained as electricity plus relativity in a way that doesn't depend on you going near light speed, since magnets work in your kitchen? Puzzle 2. How does a permanent magnet, something that sits there, fit into the moving charges picture? What's moving inside it? Puzzle 3. Why is the magnetic force sideways, always perpendicular to motion, instead of pulling straight in like electricity does? Where does that geometry come from? If we can answer those 3 without cheating, then magnetism stops being a separate magical force and becomes something tighter, a consistency requirement between observers in a relativistic universe. And then a magnet stops being a weird rock. It becomes a little everyday proof that space and time do not behave the way your intuition thinks they do. So let's earn it with the simplest magnetic phenomenon that has no magnets in it at all. 2 long straight wires, parallel, a few centimeters apart, both carrying current in the same direction. You learn the rule, same direction currents attract, opposite direction currents repel. That sounds like a brand new force law from a different universe. Now we try a different attitude. We refuse to say magnetic. We only allow ourselves one ingredient, electrostatic forces between charges, and one constraint, special relativity must be true. Here's the wire, stripped down to a cartoon. Inside each wire you have line of positive ions sitting in the metal lattice, basically at rest in the lab, a line of electrons drifting slowly the other way. In the lab frame, each wire is neutral. Positive charge density equals negative charge density. So electrostatically the wires shouldn't care about each other. Yet the wires attract when currents match. Something must be missing. Now pick a frame. Any frame. That's the game relativity forces you to play. A convenient one is the frame moving along with the electrons in wire A. Not because we can physically ride on them, but because nature must remain consistent even for imaginary observers. In that electron frame for wire A, the electrons in wire A are at rest. The positive ions in wire A are moving backward, and moving things undergo length contraction along the direction of motion, which means their spacing gets squeezed, which means their charge per unit length changes. So in this frame, the ion line in wire A looks denser than it did in the lab. The electron line is not contracted because it's at rest in this frame. Result, Wire A is no longer neutral in this frame. It looks slightly positively charged. A positively charged line creates an electric field pointing outward. That's plain Coulomb. Now what about wire B? In the lab, wire B's electrons were drifting just like wire A's, but in the electron frame of wire A, wire B's electrons are not at rest. They have some relative velocity because slow in one frame doesn't mean slow in another. Velocities add relativistically. So in this frame, wire B's ions are moving because we're moving wire B's electrons are moving too, but at a different speed than its ions. Different speeds mean different amounts of length contraction. So again, the positive and negative line densities in wire B do not stay perfectly balanced in this frame. And here's the punchline. For same direction currents, the imbalance works out so that wire B ends up with a net negative charge in this frame. So in this frame, we have something purely electrostatic. Myo wire A looks slightly positive. Myo B looks slightly negative. Opposite charges attract. The wires attract. No magnetism required. If you reverse the current in wire B, that changes which charges are moving together and which aren't. The sign of the imbalance flips, and now in the same electron frame, the two wires end up with the same net sign. Like charges repel. The wires repel. Same magnetic rule. But in this frame, it's not magnetism. It's just electric attraction or repulsion caused by relativistic changes in charge density. Now comes the part that usually makes people suspicious. You'll say this is a nice story, but the electrons drift ridiculously slowly. Length contraction at those speeds is tiny. How can that tiny effect make a measurable force? Good, because that's puzzle one. The answer is, the effect is tiny per charge, but the number of charges is enormous. A wire contains on the order of 10 quetre electrons per cubic centimeter. The electric forces between charges are huge. Normally they cancel because the wire is neutral. Magnetism is what's left over when the cancellation is imperfect in a moving frame. It's not that relativity creates a big new force. It takes a colossal force that was almost perfectly balanced and leaves a small residue. That residue is what you call magnetic. So magnetism is not a strong, separate thing. It's a correction term you can't avoid if you insist that physics looks consistent in every inertial frame. And that's why it shows up at everyday speeds. Not because length contraction is large, but because electricity is unimaginably strong and matter is unbelievably dense with charge. Now puzzle 3, why is the magnetic force sideways? Why does a moving charge near a current get deflected perpendicular to its motion instead of being pulled straight in like Coulomb? If magnetism is just electricity in another frame, you might expect it to be just another push or pull. There's a catch, and it's the catch that makes relativity feel real. In the moving frame where the force is purely electric, the force really is a straight push radially toward or away from the wire. That's ordinary electric field behavior. But when you transform back to the lab frame, you're not just transforming the force, you're transforming time. A force is change in momentum per time. If different observers slice space-time into space and time differently, then what counts as sideways acceleration versus speeding up changes too. In relativity, components of motion mix, space and time mix. So a purely electric push in one frame becomes a combination of electric and magnetic effects in another frame. The sideways nature comes from the geometry of how velocities and forces transform. You can feel this without equations if you think like this. The magnetic force depends on velocity. That already tells you it's not an independent push like gravity. It's a correction that only matters when you're moving through the electric structure of space. And it has to be sideways, because if it did work along your direction of motion, it would do work change your kinetic energy without there being a corresponding electric energy story in some other frame. The bookkeeping would break. Magnetism in classical electromagnetism does no work on a point charge. It bends trajectories, it redirects. It's like a force that is allowed to steer you but not allowed to pay your energy bill. That constraint is exactly what you'd expect from a force that is basically relativistic reshuffling of a field that does do work in another frame. Now we tackle puzzle 2, permanent magnets. A fridge magnet is not connected to a battery, yet it makes a compass swing. So where are the moving charges? Inside a magnet there are moving charges on a microscopic level, not as a net current down the length of the magnet, but as countless tiny loops. In ordinary materials, electron motions are mostly random and cancel out. In ferromagnets, iron, cobalt, nickel, something special happens. Many electron magnetic moments line up. And magnetic moment is the polite way of saying each electron behaves like a tiny current loop. Part of that is literal orbital motion of electrons around nuclei. But the dominant part in real ferromagnets is even weirder. Electrons spin, an intrinsic quantum property. It's not a little ball physically spinning, but it produces the same kind of magnetic dipole field you'd get from a tiny loop of current. Nature gives it to the electron as a built-in feature. So a permanent magnet is like a block where billions upon billions of these microscopic current loops are aligned. Their magnetic fields add instead of canceling. From far away, you see the combined field as if there were macroscopic circulating currents bound inside the material. That's why a magnet has a north and south pole. It's not that magnetic charge exists as a separate kind of substance. It's that the field lines from those loops have to close. They don't start or end the way electric field lines can charges. They wrap around. So a magnet is steady currents trapped inside matter by quantum mechanics and material structure. And now the relativity claim returns. If magnetism from a wire can be seen as electrostatics in another frame, then the magnet's field produced by those tiny currents should also be understandable as electric forces seen through a relativistic lens. But wait, because this is where people get confused. If a magnet is just moving charges, why doesn't it also look electrically charged? Why don't you get zapped by a magnet the way you do by a charged balloon? Because in the magnet's own rest frame, the positive and negative charges are arranged so that the net electric field outside is essentially zero. Just like the current-carrying wire was neutral in its rest frame. The magnetic influence appears when charges in the magnet are moving relative to you, and when you're moving relative to them, and when relativity changes how the balance of charge densities appears. So the magnet isn't a separate kind of force generator. It's an organized motion of charges where the electric parts cancel in its rest frame, leaving behind what shows up as magnetic interaction with moving charges. Now, before we go any further, we need to pin down the real problem in a way you can't wiggle out of. Because so far you could still say, fine, maybe magnetism can be explained that way for wires. But magnets attract each other even when they're sitting still. 2-bar magnets on a table pull together, no one is moving. Where does moving charge enter then? That question is the doorway. Because sitting still is only true macroscopically. Microscopically, inside each magnet, charges are in motion. Electron currents, spins align domains. And those internal motions interact with the internal motions in the other magnet. So even when the magnets are motionless as objects, the sources of their fields are not a static pile of charge. They're a structured choreography of moving charge. And once you accept that, you're forced to accept something else. A magnetic field is not an optional add-on. It's the name we give to the part of the electric influence that becomes visible whenever charges are in motion, and relativity demands consistent accounting across frames. In the next part, we're going to take one concrete setup, a moving charge near a neutral current, and walk it through both frames carefully enough that the outcome can't feel like a trick. And we'll see exactly where the magnetic field is hiding in the relativistic transformation of the electric field. So let's do that carefully. One setup, one charged particle, one wire, no poetry allowed. Picture a long wire along the table. Current to the right, that means in metal electrons drift to the left, slow drift but definite. Now put a positively charged particle next to the wire and let it move to the right, parallel to the wire. In the lab frame, you say the wire is neutral, so there's basically no electric field pointing toward or away from it. Yet the moving charge feels a sideways force toward the wire, say. You call it the magnetic force. That's the standard description. Now I change only one thing. I hop into the frame moving with the charged particle. In this frame, the particle is not moving, it's just sitting there, floating. If it's sitting there, a purely magnetic force cannot act on it. Magnetism needs motion, but the particle still accelerates. It has to, because acceleration is not a matter of opinion. Different observers can argue about speeds and times. They can't argue about whether the particle's world line bends. So in this frame, there must be an electric field pushing it. Where does that electric field come from if the wire was neutral? It comes from the fact that neutral meant positive charge per meter equals negative charge per meter. And per meter is not a sacred quantity. A meter depends on the observer. If the charges are moving, in our moving frame, both the ions and the electrons in the wire are moving, but not at the same speed. The ions were at rest in the lab. So in our moving frame, the ions stream to the left at essentially the particle's speed. The electrons were already drifting left in the lab. So in our moving frame, they stream left too, but at a slightly different speed. Not by much, but different is enough. Different speed means different length contraction. Different contraction means different linear density. Different density means the cancellation between plus and minus is no longer exact. In this moving frame, the wire gains a tiny net charge density. It might be slightly negative or slightly positive, depending on directions. The sign will match the direction of the force we call magnetic in the lab. And once the wire has net charge density, the rest is old-fashioned electrostatics. A charged line produces an electric field radial to the wire. That electric field pushes the stationary test charge. That's your acceleration. Then you go back to the lab frame and translate what happened. In the lab frame, you insist the wire is neutral, so you attribute the sideways acceleration to a magnetic field created by the current. 2 frames, 1 physical event, 2 clean descriptions that agree on the outcome. That's the core, not the slogan. Now here's the uncomfortable part you're allowed to feel. If magnetism is just electric fields seen from a moving frame, does that mean magnetic fields aren't real? They're real in the same way that east and north are real directions on a map. If you rotate your map, what used to be east component becomes a mix of east and north. But the road on the ground didn't change. Your coordinate split changed. Electric and magnetic fields are like that, except the rotation is not in space. It's in space-time. Relativity forces you to admit that space and time are not separate bins. When you change frames, you're mixing them, and the electromagnetic field is one unified object living in that combined arena. When you split that one field into electric and magnetic, you are making a choice based on your motion. Change your motion, and some of what you used to call electric becomes magnetic, and some of what you used to call magnetic becomes electric. So magnetism is not a different force, it's a different slice of the same force, and that has a strange philosophical aftertaste because it means something you probably didn't want to be true. Your everyday categories, static versus moving, electric versus magnetic, are not properties of nature by themselves. They are properties of nature plus your state of motion. Now zoom out a little. Why did Einstein care about this at all? Because Maxwell's equations, the ones that predict electromagnetic waves, already contain relativity inside them like a hidden engine. They said light moves at one speed, not one speed plus your speed. That didn't fit the old Newtonian idea of time being universal. So the universe had to pick either Maxwell is wrong or our idea of time is wrong. The experiment said Maxwell wins, time loses, and magnetism sits right at that intersection. It's what you get when you demand that electrical interactions remain consistent while time and length change between observers. That's why a magnet is not just a neat object, it's a local handheld witness to the structure of space-time. You can hold a compass next to a wire. The needle turns. That turning is telling you something about relativity, not the dramatic twin paradox stuff. The quiet everyday fact. Different observers do not agree on simultaneity, and that forces the electric bookkeeping to grow an extra term. Now, if you want to see how deep this goes, consider something almost insulting in its simplicity. If you could somehow turn off relativity, make lengths and times transform the old Newtonian way, then magnetism would collapse as a separate phenomenon. Electric forces would still exist, charges would still attract and repel, but the elegant unity would break. Light wouldn't behave, circuits wouldn't behave. The whole electromagnetic world as we know it would be internally inconsistent. Magnetism is not a bonus feature. It's the price of a universe where information has a speed limit and where physics looks the same to different observers. And that should change how you look at force in general. We're used to thinking of forces as invisible hands. Gravity reaches out, electricity reaches out, magnetism reaches out. But the modern picture is harsher and cleaner. There are fields. A field is a condition of space that tells charges and masses how to move, and the division of that field into parts depends on your motion through it. The world is not built from separate forces stapled together. It's built from unified structures that your mind labels differently depending on how you're moving. That's why the sideways nature of magnetism stops looking arbitrary. It becomes almost inevitable. It is the part of the electromagnetic influence that shows up when you change frames, the part that keeps the energy and momentum accounting consistent across space-time. So what does that mean for you standing in a kitchen, sticking a magnet to a fridge? It means you're not looking at a different kind of force. You're looking at the same old electric interaction but arranged by quantum mechanics inside matter into steady microscopic currents. And you're looking at what that interaction must become when the universe refuses to give you a universal clock. A magnet is a relativistic object even when it's cold and still and boring. Not because anything is moving fast, because the rules of measurement are, and that's the real closing thought. Relativity is not something you visit when you accelerate to near light speed. It's the underlying grammar of measurement that is always there, even when the numbers are small. Magnetism is one of the places that grammar leaks into daily life. If you can explain that to someone else without hiding behind formulas, you're already doing real physics. If you want to keep going with this way of thinking, stay with the channel. Not for more facts to memorize, but for more moments where obvious turns out to be a costume reality is wearing.